Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is pneumatic directional control valves. Our objective is to examine pneumatic directional control valves and discuss their function in pneumatic systems. Additionally, we'll examine port numbering schemes common in the pneumatics industry. This lecture operates under the presumption that the viewer has a prior level of familiarity with hydraulic directional control valves as illustrated in the Hydraulic Directional Control Valves lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, only dimly recall its contents, please take the time to do so now. Operating from this base of prior experience, this lecture will be a brief review of the aforementioned topics and largely will restrict itself to discussing properties unique to pneumatic valves. Since the pneumatic directional control valve family is so numerous, I thought it'd be wise to first examine them independently rather than including them in a larger lecture on pneumatic schematic symbols. As with any lecture, the content herein depicts standards adopted by a majority of modern manufacturers, but not all. A thick, tangled jungle of peculiarities exist, especially for older valves and valves manufactured by shoddy companies in backwards countries. Canada, I'm looking at you. Always consult the datasheet for the directional control valve of interest. As you're no doubt aware, a valve is a fluid power component designed to modify pressure, flow rate, or flow direction. A subset of these valves, those that modify flow direction, are appropriately called directional control valves. The purpose of a directional control valve is to stop, start, and change direction of flow in a fluid power circuit. Flow direction ultimately influences the actuation direction of a fluid power actuator. Directional control valve position influences whether pneumatic cylinders extend, retract, or stay put, as well as the rotational direction of pneumatic motors. Three properties define directional control valves: ports, positions, and actuation method. A port is a defined connection point. A position is one defined function of a valve characterized by a particular flow path. Lastly, the actuation method is how a valve is moved from one position to another. Astute observers will note that I have not made use of the nonsense term way, principally because the term way might mean ports in one industry or synonymous with the term position in another. It is for this reason I have declared the term way officially dead. In lieu of condolences, the Way family has requested you send a large monetary donation to the author of the Big Bad Tech channel. Consider this 2x2 or 2-port, 2-position, solenoid actuated, spring offset directional control valve. Ports are the entry and exit points to a valve. Since this schematic symbol has two paths leading to or from it, this directional control valve has two ports. We'll return to port labeling conventions unique to pneumatics in a moment, but for now, let's just call them 1 and 2. In the position on the right, passage from 1 to 2 is closed, as indicated by the block T's. The spring on the right-hand side ensures the directional control valve is offset into this closed position in the deactivated state. For this reason, one might also refer to this directional control valve as a 2x2, solenoid-operated, normally closed directional control valve. Normally closed is sometimes abbreviated NC. In contrast, the position on the left will allow passage from port 1 to 2, as indicated by the arrow pointing from 1 to 2 in the position box. Single-headed arrows in a position box means flow is intended to be unidirectional, whereas double-headed arrows mean flow can be bidirectional. To move the valve into the activated left-hand position necessitates the valve be actuated by some outside source, as identified by the solenoid operator on the left-hand side. Energizing the solenoid moves the actuated directional control valve to the activated open position, allowing passage from 1 to 2. When the solenoid is de-energized, the spring offset on the right-hand side will return the directional control valve to the deactivated closed state, blocking passage from 1 to 2. The internal construction of pneumatic directional control valves is startlingly similar to that of hydraulic directional control valves, whereby moving internal components like poppets, sliding plates, or spools selectively connect or disconnect ports via the internal passageways machined into the valve body. A simplified internal diagram of a 2x2 normally closed directional control valve might look something like this. In the deactivated state, the spring offset on the right-hand side positions the sliding spool such that a land or a high point on the spool blocks passage from 1 to 2. Whereas in the activated state, the energized solenoid on the left-hand side pushes the sliding spool such that a valley or a low point on the spool allows passage from 1 to 2. When the solenoid is de-energized, the spring offset returns the spool such that the land again blocks passage from 1 to 2. Let's build upon and modify this valve. Consider the following subtle modification you might find in a pneumatic system. Rather than using a wound coil of wire as a return spring, one might also encounter air springs, whereby a directional control valve makes use of pressurized air on the side of the spool to assert the deactivated closed state. As with a coil spring, in the absence of an electrical signal to the solenoid, the air spring pushes the valve into the deactivated closed state. Energizing the solenoid overcomes the air spring, and the actuated valve moves to the activated open position, allowing passage from 1 to 2. When the solenoid is de-energized, the air spring again returns the valve to the deactivated closed state, blocking passage from 1 to 2. You'll note the only way of shifting this solenoid-operated valve, as presently illustrated, to the activated open position is via an electrical signal. Oftentimes, the technician needs to force a valve into a desired position for troubleshooting or emergency purposes, or in the event of loss of electrical function. For this reason, manufacturers often include an accessory manual actuator as a means of overriding the electrical solenoid. Appropriately enough, these are called manual overrides and are schematically symbolized as a top hat next to a solenoid. Even if the control circuit is depowered and no electrical signal reaches the solenoid, an operator can still physically push the directional control valve into the activated position. Manual overrides often take the form of a push or a pull operator, or even small screws that can force a particular valve into a desired position and lock it in place. A manual override is essentially a means of offering a technician a means of shifting a directional control valve to some desired position should the solenoid or control system fail to do so. Starting with the previously discussed 2x2 or 2-port 2-position solenoid actuated normally closed directional control valve, including a manual override and air spring offset, consider the significant consequences of this subtle but very important change. Notice anything different? This new valve is still a 2x2 or 2-port 2-position directional control valve that's solenoid actuated with a manual override and an air spring offset. Only this version's deactivated state opens the passage from 1 to 2. When energized, the solenoid slides the spool such that it closes passage from 1 to 2 in the activated state. For this reason, this particular valve on the right might be referred to as a normally open 2x2 solenoid actuated valve. Normally open is sometimes abbreviated as NO. I must emphasize that these are two entirely different directional control valves with fundamental behavior differences between them. The directional control valve on the left is normally closed, and in the deactivated state blocks passage from 1 to 2. Whereas the directional control valve on the right is normally open, and in the deactivated state allows passage from 1 to 2. When the solenoids are energized by an electrical signal, these directional control valves change states. The directional control valve on the left opens the passage from 1 to 2 in the activated state, whereas the directional control valve on the right closes passage from 1 to 2 in the activated state. I don't mean to be overly dramatic, but misinterpreting a schematic symbol can have life-threatening consequences, like turning on the flow of poisonous gases like tungsten hexafluoride when you mean to turn it off, or turning off oxygen supply to a spaceship when you mean to turn it on. Don't make these easily avoidable mistakes, and be sure you know what the deactivated and activated states of a directional control valve imply to a larger pneumatic system. While we're on the topic of actuators, a veritable freak show of different style actuators exist, including, but not limited to, manual actuators like push buttons, pull buttons, levers, knobs, and foot pedals, mechanical operators like bidirectional and unidirectional rollers, springs and air springs, pneumatic pilots, and various types of electrical solenoids. All manual operators necessitate an operator use their hand, foot, or some other sufficiently robust portion of their anatomy to push, pull, flip, twist, or otherwise diddle or dork with some operator intended for human use. Mechanical actuators, in contrast, are intended to strike some tag or some limit device in an automatic system without human intervention. Valves can also use pilot air pressure signals from somewhere else in a pneumatic system to shift a directional control valve spool to a desired position. Depending upon manufacturer and country of origin, I've seen air pilot actuators schematically illustrated as a dashed line leading to a box with an empty arrow, a dashed line leading to an empty arrow without the box, or just a dashed line without an arrow or a box. We'll examine air pilot pneumatic directional control valves and applications in greater detail in later lectures. Lastly, solenoids might be illustrated as simple on-off style solenoids, as in our previous examples, or as variable solenoids as part of a more sophisticated proportional valve. Without getting too detailed, a simple on-off style solenoid, as the name implies, operates digitally, and does or does not fully shift a valve into another position depending on the presence or absence of a full voltage signal. In contrast, a variable solenoid operates using a continuously variant analog signal where application of full voltage still fully shifts the valve as previously. However, application of half voltage half shifts the valve. In this manner, a variable solenoid as part of a proportional valve with a specially designed spool not only operates as a directional control valve, stopping, starting, and changing the direction of fluid flow, but also as a flow control valve by ramping up or throttling down flow rate, thus controlling not only actuator direction, but also actuator speed. We'll examine proportional valves in much later lectures. Lastly, I should mention combination of these types of actuators exist. For example, consider a solenoid actuated valve that rather than directly shifting the spool electrically, as in our previous examples, instead, the electrical portion opens up a small air pilot passage and pilot air does the actual hard work of shifting the spool. As one might expect, these types of indirectly acting solenoids might be illustrated as a combination of a solenoid and air pilot symbol. Before we move on, let's discuss the consequences of directional control valves without springs, coils, or air. You'll recall these accessory devices offset two-position directional control valves into some desired deactivated state. Directional control valves with offset springs are sometimes called monostable, meaning there is a preferred deactivated state the directional control valve returns to when it isn't being actuated. In this example, this monostable 2x2 directional control valve has a preferred normally closed deactivated state and only opens at the direction of the lever. Once the valve isn't being actuated, the spring offset valve immediately returns the valve to the deactivated closed state. This isn't always necessary or desired. You might find certain directional control valves making use of actuators with detents, or pairs of actuators operating in opposition to one another. For example, consider a 2x2 directional control valve lacking an offset spring, employing a manual operator with a detent, illustrated as a triangular cutout. Alternatively, a detented actuator might be illustrated as a regular actuator on one side with a detent on the other. When an operator twists a detented knob, pushes a detented button, or pulls a detented lever, the directional control valve moves into the opposite position and then just stays there until an operator makes the conscious decision to twist, pull, or push the detented actuator in the opposite direction, and the directional control valve moves back and stays there. There's no need for a return spring because these types of directional control valves maintain the last asserted state. In contrast to valves with a preferred deactivated state, these types of valves might be called bistable valves, i.e. valves with two stable states. The classic example of these types of bistable directional control valves is a very simple inline shutoff valve or a shutoff valve on a compressor. Turn the lever one way and flow is blocked. Turn the lever the other and flow is allowed to pass. Open it and it stays open, close it and it stays closed. Depending upon your country of origin, you might find simple shutoff valves like this schematically illustrated as a pair of opposing triangles. Bistable directional control valves can also make use of paired actuators operating in opposition to one another. Consider a 2x2 double air piloted valve. Look, no spring. When a signal is sent to the air pilot on the left, the directional control valve moves into the open position on the left and allows flow from 1 to 2. In contrast, when a signal is sent to the air pilot on the right, the valve moves into the closed position on the right and blocks flow from 1 to 2. The air pilots essentially push the valve into a desired state, and it stays there till the opposite pilot asserts itself and moves it back. Inquisitive viewers might ask, what's the deactivated state for this type of valve? Come to think of it, what's the activated state? Is there one? Also, what happens if both pilots receive a signal? Dear viewer, I'd love to answer these legit quandaries about memory, priority, and more, but seeing time is of the essence, you'll just have to wait till I publish an upcoming lecture on air-piloted valves. Anticipation, as they say, conspicuous pause, is part of showmanship. Let's now examine 3x2 directional control valves, where the first number 3 is the number of ports, 1, 2, 3, and the second number 2 is the number of positions, i.e. the deactivated and activated state. Consider a normally closed 3x2 push-button operated directional control valve. In the deactivated state, the spring offset places the spool in the closed position, such that flow from port 1 to 2 is blocked. However, port 2 is dumped to an exhaust port on 3, schematically represented as an empty arrow pointing away into the external environment. Exhaust ports are often located in the bottom of the valve body at the point of use. You may or may not see a muffler or a silencer on the exhaust port schematically illustrated as this maze-like zigzag passage designed to minimize the sound of escaping air. When an operator pushes the push button, the spool would be moved into open position such that flow passes from 1 to 2, and 3 is blocked. When an operator releases the push button, the valve returns to the spring offset closed state, blocking 1 to 2 and dumping 2 to 3. Now let's compare a normally closed 3x2 directional control valve with the previously discussed normally closed 2x2 directional control valve. Both valves block passage from 1 to 2 in the deactivated state, and when manually activated by an operator, move to an open position, allowing flow from 1 to 2. At first glance, they might seem indistinguishable from one another, but don't be fooled by the superficial similarity in function. The key difference is the exhaust on port 3. In the deactivated state, a normally closed 2x2 valve allows no reverse passage from 2 back to the external environment, whereas a deactivated state of a normally closed 3x2 valve does. Depending upon application, one might choose one valve or another. For example, one might use a normally closed 2x2 valve to isolate one leg of a pneumatic system from another. However, it's not a good choice for actuator control. For example, a normally closed 2x2 valve could be used to extend a spring return pneumatically extended single acting cylinder. However, once extended, it wouldn't retract, even in the deactivated position, because pressurized air remains trapped in the cap end of the cylinder. A normally closed 3x2 valve would probably be a better choice. In the deactivated state, the cap end is exhausted to atmosphere, allowing the spring on the rod end to retract the cylinder. In the activated state, the valve allows pressurized air to enter the cap end of the single acting cylinder, and the cylinder extends. When an operator releases the push button, the valve returns to the deactivated state, dumping the cap end to the atmosphere, allowing the spring on the rod end to retract the rod. Let's take a closer look at this particular push button operated 3x2 normally closed directional control valve. We can see the muffler on exhaust port 3. I really like this particular directional control valve because it's rather easy to customize. We look at the valve body from the side, we can see how the push button operator interacts with the spool. In the deactivated state, the spring offset keeps the spool in the desired position. When an operator smashes the push button, the spool moves into the open position. When an operator releases the push button, the spring offset returns the valve to the deactivated position. The way this particular valve is constructed, it's a trivial matter to pop off the push button operator and install another style of actuator, for example, a selector switch with a detent. Now you don't have to pay some homeschooled operator $7.25 an hour to stand around all day holding a push button down. Additionally, check out the writing on the bottom of the valve body. Input port 1 is labeled normally closed. Exhaust port 3 is labeled normally open. It's again a trivial matter to completely change the function of this directional control valve by popping off the muffler on 3 and swapping it out with the elbow on 1 and vice versa, and calling this a selector switch actuated, normally open 3x2 directional control valve. Can you dig it? Shoot, this valve is so radically different now, its mama wouldn't even recognize it if it walked in the front door and said hello. Compare and contrast the behavior of these two valves and a single acting cylinder. 1, the original normally closed configuration, and 2, the modified normally open configuration. The valve on the left is normally closed, and in the deactivated state, the cylinder is retracted. In contrast, the valve on the right is normally open, and in the deactivated state, the cylinder is extended. If an operator presses the push button on the valve on the left, the cylinder extends. Whereas, if an operator activates the selector switch in the valve on the right, the cylinder retracts. As I cautioned you earlier, proper interpretation of schematic symbols can save your life. In every respect, these two valves are diametrical opposites of one another, and misinterpretation of their schematic symbols can have dire life-threatening consequences. 3x2 valves can also be used as selectors. For example, consider a pneumatic system served by a primary and a backup pneumatic power source. In ordinary operation, the primary system powers a circuit. In the event a primary system fails or necessitates service, 3x2 valve can be moved into a position such that the backup pneumatic source takes over. Similarly, a 3x2 valve can also be used to select output. For example, a 3x2 valve can be used to select a desired branch circuit for a single source. In ordinary operation, the 3x2 valve routes pressurized input to circuit A. When circuit A finishes the task, the 3x2 valve can be moved into a position such that the same source now services circuit B. 3x2 directional control valves can also control double acting cylinders. Consider a pair of normally closed 3x2 directional control valves used to control a double acting cylinder. In the deactivated state, both cap and rod end are exhausted to atmosphere, and the cylinder rod would float freely. When an operator pushes the push button on the valve on the left, pressurized air enters the cap end of the cylinder and the cylinder extends. When an operator releases the push button on the valve on the left, the cylinder remains extended. However, both cap and rod end remain exhausted to atmosphere and the cylinder rod would float freely. When an operator presses the push button on the valve on the right, pressurized air enters the rod end of the cylinder and the cylinder retracts. As previously, when an operator releases the push button on the valve on the right, the cylinder remains retracted. However, both cap and rod end remain exhausted to atmosphere and the cylinder rod floats freely. What happens when an operator presses both push buttons? Pressurized air is routed to both cap and rod end. More area on the cap, less on the rod end. The cylinder extends, although it does so with a reduced force because the rod end acts in opposition to the cap. If this seems a little wasteful to use two valves to control one cylinder, you got a point. For this reason, manufacturers offer other types of valves with increased functionality. Consider a 5x2 directional control valve. 5x2? Some of you might be like, wait, what? Why are you skipping from 3 to 5 without talking about 4? Trust me, after we discuss 5-port directional control valves, I'll explain why 4-port directional control valves aren't nearly as popular in pneumatic systems. This particular 5x2 directional control valve has 5 ports, 1, 2, 3, 4, 5, and 2 positions, a deactivated and activated state. It appears to be lever operated. A spring offset on the right-hand side pushes the spool into a deactivated state, whereby pressurized flow at 1 is routed to actuator port 2, and actuator port 4 is dumped to exhaust port 5, and port 3 is blocked. When an operator actuates the lever, the spool moves into an activated state, whereby pressurized flow at 1 is routed to actuator port 4, and actuator port 2 is dumped to exhaust port 3, and port 5 is blocked. This particular 5x2 directional control valve would be a great choice for controlling a double-acting cylinder. In the deactivated state, pressurized flow at 1 is routed to actuator port 2. Pressurized air enters the rod end of the cylinder. Actuator port 4 is dumped to exhaust port 5. The cap end of the cylinder is exhausted to atmosphere. The cylinder retracts. When an operator actuates the lever, the spool moves into an activated state where pressurized flow at 1 is routed to actuator port 4. Pressurized air enters the cap end of the cylinder. Actuator port 2 is dumped to exhaust port 3. The rod end of the cylinder is exhausted to atmosphere. The cylinder extends. When an operator releases the lever, the spring offset valve again returns to the deactivated state and the cylinder fully retracts. In this fashion, a single directional control valve fully extends or fully retracts a double-acting cylinder based on the actuation state of the manually operated lever. Before we continue on, it's probably a good point in this lecture to discuss port numbering and naming conventions. The observant among you might be noticing a pattern. 1 is always pressurized supply input. 3 and 5 are always exhausts. And 2 and 4 are always actuator ports. Evens on the top, odds on the bottom. This is not a coincidence, and most manufacturers follow the standard naming convention. Most. You might encounter some manufacturers or older valves employing letter designations for the ports, as is common in hydraulic valves. Port 1, the pressurized input, might also be called P. Actuator ports 2 and 4 might be called actuator ports A and B. The letter designation for exhaust ports varies widely. They may be called E, X, or R. Don't ask me why it's R, I don't know. Additionally, they may be called XA and XB, or EA and EB, or RA and RB, indicating which particular actuator port is being exhausted to the atmosphere. You'll recall a lot of hydraulic directional control valves use this letter designation PT, A, and B, pressure, tank, A and B actuator ports, so it's pretty understandable. The one variation being, rather than a single T return connection, as is common in hydraulics, most 5x2 directional control valves have independent exhausts for each actuator port. Which brings me to a point where I can explain why 4-port valves aren't as common as 5-port valves in pneumatic systems. As you'll soon learn, actuator speed control in a pneumatic system is a serious pain in contrast to a hydraulic system, principally because the power transfer medium of choice central to pneumatic systems, air, is compressible and occupies different volumes at different pressure and temperature conditions. This means actuator speed control via various flow control methods is a pretty involved task for pneumatic systems and often necessitates access to both upstream and downstream, i.e. pressure and exhaust, for independent actuator ports. Long story short, ports 3 and 5 might not be directly exhausted to the environment, and accessory components might be between the directional control valve and the actuator or exhaust. For now, just realize a 5x2 directional control valve, i.e. a valve with independent exhausts for each actuator port, sure makes it a lot easier to meet these challenges, whereas a 4-port valve, one with a shared single exhaust, would only complicate it. Additionally, we'll examine accessory components like quick exhaust valves in later lectures. Additionally, I should mention that actuators and springs might be numbered, where the number is indicative of a function. For example, consider a lever-operated normally closed 2x2 directional control valve, where 1 is again our supplied input and 2 is our actuator port. This directional control valve might have 1 0 on the offset spring and 1 2 on the lever. 1 0 on the offset means 1 is blocked, i.e. the deactivated normally closed state asserted by the offset spring, where 0 essentially means blocked. 1 2 on the lever means when the lever is actuated, 1 is passed to 2. Similarly, consider a lever-operated normally closed 3x2 directional control valve. It might also say 1 0 on the spring and 1 2 on the lever, again meaning the offset spring blocks 1 in the deactivated state and the lever passes 1 to 2 in the activated state. In contrast, a lever-operated normally open 3x2 valve might say 1 2 on the spring and 1 0 on the lever, meaning the offset spring passes 1 to 2 in the normally open deactivated state and the lever blocks 1. In keeping with this standard, the actuators on a push-button operated 5x2 directional control valve might have the following numbering: 1 2 on the spring offset and 1 4 on the lever, meaning the offset spring passes 1 to 2 in the deactivated state and the lever passes 1 to 4 in the activated state. After some repeat exposure and practice with a numbering system, you won't even need the schematic symbol to determine a valve's function. This being said, the schematic sure helps out. Lastly, let's take a look at 3-position directional control valve. The previous example, featuring a 5x2 directional control valve controlling a double-acting pneumatic cylinder, was limited to 2 choices, either full extension or full retraction with no midpoint option. A 5x3 directional control valve allows this increased functionality. Consider a double solenoid actuated 5x3 directional control valve spring-centered to a closed position where all ports are blocked. If we were to hook this up to a double-acting cylinder in the following fashion, the closed center position, when neither solenoid is energized, would lock the actuator in place with the blocked ports. If solenoid 1 4 on the left-hand side is energized, it would move the spool to a position whereby pressurized flow at 1 is routed to actuator port 4. Pressurized air enters the cap end of the cylinder, and actuator port 2 is dumped to exhaust port 3, and the rod end of the cylinder is exhausted to atmosphere. The cylinder extends. Whereas if solenoid 1 2 on the right-hand side was energized, this would move the valve to a position whereby pressurized flow at 1 is routed to actuator port 2, and pressurized air would enter the rod end of the cylinder. Actuator port 4 would be dumped to exhaust port 5, such that the cap end of the cylinder is exhausted to atmosphere. The cylinder retracts. Again, when neither solenoid is energized, the 2 centering springs on either side of the valve push the 3-position valve into a closed center position where all ports are blocked. In this fashion, a system could partially extend or partially retract the cylinder with solenoid 1 4 or 1 2, and then deactivate it at the appropriate time to hold the cylinder in a locked position midway between full extension and full retraction. The blocked actuator ports 2 and 4 ensure the cylinder remains in this position, albeit with a little spongy give common to pneumatic systems. Other types of center positions exist. If locking an actuator in place isn't the best choice, one can also make use of one type of a float center, whereby actuator ports 2 and 4 are both exhausted to atmosphere. The behavior of this 5x3 directional control valve with a float center is otherwise identical to the closed center, the one exception being in the deactivated state, the cap and rod end are open atmosphere, which allows the rod to float, hence the name, freely. This could be handy if an operator had to manually position the rod for some variable size load. As with the previous 5x3 directional control valve, you'll note 3-position directional control valves necessitate not one offset spring, but rather 2 centering springs to assert the deactivated state. All right, that is that. We'll examine air-piloted pneumatic directional control valves and more in later lectures. In conclusion, this lecture will examine pneumatic directional control valves. We learned a directional control valve stops, starts, and changes airflow direction in a pneumatic system, ultimately influencing the direction of a pneumatic actuator. We discussed ports, positions, and actuation methods, and examined simple applications of 2x2, 3x2, 5x2, and 5x3 directional control valves in pneumatic systems. Lastly, we discussed port numbering schemes common in pneumatics industry. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.